Video 4: Understanding the Sun and Solar Energy. The Sun lies in the center of our solar system, approximately 93 million miles from the Earth. Composed primarily of hydrogen and small amounts of helium, the Sun is a massive fusion reactor. The Sun's core intense pressure and heat force hydrogen atoms to unite or fuse, creating slightly large helium atoms. In this process, immense amounts of energy is released. This energy migrates to the surface of the Sun and then radiates out into space, primarily as light and heat. Solar radiation streaming into space strikes the Earth, warming and lighting our planet and fueling aquatic and terrestrial ecosystems. According to a French energy expert, the solar energy received each year by the Earth is roughly 10,000 times the total energy consumed by humanity. To replace all the oil, coal, gas and uranium currently used by the human society with solar energy, we need to capture only a mere 0.01% of the energy from the sunlight striking the Earth each day. According to the US Department of Energy's National Renewable Energy Laboratory, to generate the electricity the United States consumes, we only need to install solar panels on 7% of the total land surface area currently occupied by the cities and homes. We could achieve this by installing PVs on rooftops, over parking lots, and on the sides of buildings. Understanding solar radiation. The Sun's output is known as solar radiation. Solar radiation ranges from high energy short wavelength gamma rays to low energy long wave radiation known as radio waves. In between these extremes, starting from the short wave end of the spectrum, are X-rays, ultraviolet radiation, visible light and heat. While the Sun releases numerous forms of energy, most of it, about 40%, is infrared radiation, heat or visible sunlight. Traveling at a speed of 1,86,000 miles per second, solar energy takes 8.3 minutes to make its 93 million mile journey from the Sun to the Earth. Solar radiation travels virtually uninterrupted through space until it reaches the Earth's atmosphere. In the outer portion of the atmosphere, a region known as stratosphere, ozone molecules in the ozone layer absorb 99% of the incoming ultraviolet radiation, dramatically reducing our exposure to this potential harmful rays. As sunlight passes through the lower portion of the atmosphere, the troposphere, it encounters clouds, water vapor and dust. These may absorb the Sun's rays or reflect them back into space, reducing the amount of sunlight striking the Earth's surface. Irradiance. The amount of solar radiation striking a square meter of the Earth's atmosphere or the Earth's surface is known as irradiance. It is measured in watts per square meter. On a clear day, nearly 30% of the Sun's radiant energy is absorbed and converted into heat or reflected by dust and water vapor in the Earth's atmosphere. By the time the incoming solar radiation reaches a solar array on a roof, the incoming solar radiation is reduced to about 1000 watts per square meter. Solar irradiance. Solar irradiance varies during daylight hours at any given site. At night, solar irradiance is zero. As the sun rises, irradiance increases, peaking around the noon. From noon until sunset, irradiance slowly decreases, falling once again to zero at night. These changes in irradiance are determined by the angle of the sun's rays, which changes continuously as the earth rotates on its axis. The angle at which the sun's rays strike the earth affect both the energy density and the amount of atmosphere through which sunlight must travel to reach the earth's surface. Let's start with energy density. As mentioned, low angle sunlight delivers much less energy per square meter than high angle sunlight. The result is a decrease in energy density. Early in the morning, irradiance is low. As the sun makes its ways across the sky, however, irradiance increases. Irradiance is also influenced by the amount of atmosphere through which the sunlight passes. The more atmosphere through which sunlight passes, the more filtering occurs. The more filtering the sunlight makes it to the earth, the lower the irradiance. Irradiation. Irradiance is an important measurement, but the term most installers need to know is irradiance over time, the amount of energy they can expect to strike a PV array. Irradiance over a period of time is referred to as solar irradiation. It's expressed as watts per square meter striking the Earth's surface or a PV module over a period of time, usually an hour or a day. For example, solar radiation of 500 watts of solar energy striking a square meter for an hour is 500 watt hours per square meter. Solar radiation of 1000 watts per square meter over 2 hours is 2000 watt hours per square meter. To help keep irradiance and irradiation straight, you can think of irradiance as a measure of instantaneous power. Irradiation, on the other hand, is a measure of power over a period of time, therefore a measure of energy. Irradiance is a single black line, the number of watts per square meter at any moment in time, the area under the curve in solar irradiation. Knowing an area's solar irradiation is useful for professional installers and do-it-yourselfers when sizing a system. And here ends video 4, Understanding the Sun and Solar Energy.